be on the whiteboard or whatever it is that I'm sharing. And so I'm going to do that, stop the video, and hopefully everyone can still hear me. And so what I'm going to do is just kind of quickly go through the changes for the rest of the semester. So I guess the first big change is I decided to basically cancel the project, the group project, and instead I made that extra credit, and I kind of updated a few things with respect to that. So like some of the due dates and so on. So and then I think I was pretty generous with respect to this. I don't know if I put it, I thought somewhere I did. I think I maybe said it somewhere else. So if you do the project, then I think it's worth up to 5% of your final grade in extra credit. Okay, so it'd be like half of an exam or something like that, half of a grade. I'd really encourage people to at least consider doing the extra credit, just because it's kind of fun to do this, and you put a lot of work into the MyPL stuff. So extending it is really enjoyable and rewarding. But given everything else going on, I totally understand if people don't have the time or it's just too complicated to do in a team setting. So it still would be a team-based project. You don't have to do it in a team, but I would prefer that. So then I added in our extended spring break. So that was week 9 of the class. So basically we just lost that time. And then the rest
Did you say
of
if
the
it's worth as much
schedule
extra
is
credit
just
as the
kind of my
original
goal
project was
for
worth?
getting through things till the end of the semester. So homework
I mean, I'll have a look at it.
6 is due on
Did you say there's a max
Thursday.
group limit?
And in terms of turning in the homework, all of it should be submitted through the
Okay.
GitHub Classroom.
Which I think could include all of us.
I think the group limit is 3 or 4, so
we're
we're
going to
good.
be somewhat flexible with respect to when those things get pushed. So as long as you are getting stuff in the day that it's due, that is fine. It doesn't have to be pushed like right before class. I'm not going to be checking that, etc. So homework, I think some folks are still working on homework 5. So both homework 5 and 6 would be due this Thursday. And then I'll push out homework 7 on Thursday, which will finish up the evaluation part. And you'll have a week and a half about to finish that. Homework 7 is actually probably is like the easier one to some degree, although you're doing more complicated things. But I'm going to talk more about that and what's involved on Thursday. And then we still had 2 exams that were scheduled for the class. And so my plan is, as of now, to make those both take-home exams. So the basic idea will be after the class next Tuesday, I'll kind of release the exam on Blackboard, and it will be a timed exam. So you'll have a certain fixed amount of time to do it, but you can do it anytime from when I release it to the following Tuesday. So if you want to do it over the weekend, that's totally fine, or some evening or in the morning or whatever. You can
Oh
do
my
that
god, these are going to be such hard tests, probably.
And,
absolutely.
The exam will be open
book, open notes.
And it will be timed. So
yep.
Oh, right.
So anyway, so that's how I'm planning on doing the exams.
So they're going to be brutally hard and timed.
Today and next week, we're going to be really very heavily switching gears into talking about functional programming using Haskell. So much of the rest of the semester is really going to be that. We'll move fairly quickly through things, and the assignments will be kind of reflective of that to some degree. They'll be programming assignments, but my guess is for most folks, they're not going to be as hard as these last couple MyPL assignments. They won't be as involved. It won't be as time consuming, but it'll be different and will require some thinking because it's a new language and it's a very different language than probably languages you've seen. And then, so we have a fairly accelerated schedule through Haskell. And then I want to at least just kind of expose you or kind of give you a sense for logic programming. So I'll be talking about, I'll save some time to talk about a specific style of logic programming, and there'll be one homework assignment associated with that. Depending on how far we get, that might be very simple or might be a little bit more involved, but that one shouldn't be too bad. And then finally, we'll have the final, and I think we'll do something similar with respect to Blackboard for the 2 exams for the final, but I would like to have it during the actual final exam time that we have scheduled for the class. Does anyone have any questions?
It's just like the real class.
Okay.
So about your office hours, are they going to be like one-on-one video chats or?
Yeah, good question. So what I'm going to do for office hours is I'm going to so there's kind of, at first I wanted to do it so that there's a waiting room. So then in Zoom, if you have a waiting room, people can enter the waiting room and then you kind of let people into office hours that way. It isn't, it doesn't seem very, there's some issues with that I found today, in that like I couldn't connect my my iPad up to the, I don't know what was going on with that. I couldn't get that to work with the screen sharing. And then people kind of come late and I missed that in the first class. And then sometimes people drop and come back in. So it's just kind of a mess for that. So I think for now it'll just be open. And then certainly if people would like to meet with me one-on-one, we can set that up specifically to do that. And then there is a way to kind of like put other people on hold. So we can also do that if we want to do one-on-one stuff. So I think, but for the most part, it'll kind of just be open. And I might, one thing I've been thinking about, I just don't know quite how to schedule it, is to have maybe some kind of like extended office hour a week or whatever, where it's more of a discussion section. So people can ask questions just related to like 326. I'm just not sure when to schedule that such that everyone can participate. And so, so anyway, if people have ideas of how to do that scheduling or how to do that, please let me know. And I'll keep thinking about how to do that, how to work that in with my own personal schedule. Long answer. Any other questions? So the other thing I'm going to try to do is be a little bit more proactive in posting the, okay, well, I didn't do it this time. I'm posting the lecture notes ahead of the schedule. So actually I can do that, I think, real quick. Well, I'll hold off on that. So I'll try to post the lecture notes prior to the lecture. So if you want to, you can be looking at the lecture notes kind of at the same time. I'll lecture off the notes, but I'm going to use this whiteboard application or the note-taking application instead of just directly talking about the lecture notes. Okay. So today I failed on that, but I'll, as we go on, I'm going to make sure I try to post stuff ahead of time more. Okay. Any other questions with respect to the structure of the class or how things are going to work? I guess the other thing I didn't mention is
Wait,
I
two
will
part B.
try to include a couple quizzes
The
still.
maximum of two part
And
B
so
is
those, again, I'm
infinity.
going to do very similarly to the exams where you can
And
do
the
it
math homework.
offline or out of band asynchronously with the class.
I'm having a look at
and
it,
then,
and
but
two
they'll be
part
timed
B
again. And
is
open
the
note.
maximum is
So I think
infinity.
from now on, all the exams and everything are going to be open book, open note.
As A approaches 0, it's gonna go to infinity.
Okay. And again, if you do have questions, please ask. And just you can unmute and ask the question or use the chat. All right, so this is the plan, my plan for today.
Reveal
I did
yourself.
kind of the course overview, and then, whoops, let me fix this. This should say wrap up. So I'm gonna, where we stopped last time, we were talking about lambda calculus. So lambda calculus is like a Turing machine. It's kind of the foundational model or computational model for functional programming. So we went pretty far. I'm going to kind of start back at the beginning and go through that stuff a little bit quicker because we've touched on it already, but then kind of wrap that up. And in particular, I wanted to show you that you can do looping in functional calculus, and you do that through recursion. And so kind of combined, this notion of being able to do Boolean expressions and recursion kind of gives you all of the power of Turing machines. I'm not going to go into many detail just to give you a detail about that, but just to give you a sense for this. Okay, and then this will lead into the Haskell, which is going to be a brand new, for most people or for many people, a brand new programming language. And I'm going to talk about some of the features of Haskell to start with. And then just if we get there, just show you a little bit kind of how to get going, how to use the system that we're going to use. Okay. All right, so just as a refresher for lambda calculus, so lambda calculus comes built in with this idea of unnamed single argument functions, and those are called lambda functions. So here's a couple examples that we did last time of lambda functions. So the first one is what we're calling the identity function. So basically, it takes as an argument, the symbol lambda denotes that this is a function, a lambda function. It takes a single parameter or a single argument, in this case x, we're calling that argument x. And then the period basically says everything after this is the body of the function. And the body, in this case, just is x itself. So one way to think about this is the function takes an x and then returns the value of the x. Okay. So this is like the simplest lambda function. Here's a more complicated function where we have a lambda function, and it, again, just takes one argument. We're calling that x. And then the body of the lambda function is another function that gets returned. And that function takes a y and then returns the x. Okay, it's a little weird, but it's as if it's very similar to a function. The whole thing is similar to a function that takes two arguments and then just returns the value of the first argument. Sometimes, for convenience, we write this long form where it's a lambda function that returns another lambda function using this shorthand syntax, where it looks like the lambda function takes 2 arguments and then it returns the first argument. But this is really just shorthand for this longer form. And in fact, what we'll see is this is exactly how Haskell works. When you have a function that looks like it takes 2 arguments, it really converts that into a function that can return a function, which is a little weird. But we'll get into that more later. Okay, so this is at the core of lambda calculus, is our lambda functions. And then there's this notion of function application, okay, which is just a fancy way to basically say you pass something into a function and then you get the result back. So you take a value and you apply it into the function or something. So here's one example where we take this very simple identity function and we have a value 0, and we just basically we put parentheses around the function, and then we put the value we're going to pass in. So this whole thing together is what's called a function application. And the basic idea of how this works is if you are going to do the actual, like call the function on the value, you take the 0, you pass it in as the first parameter, and then x would get replaced with 0, and the result would just be the body, which is x, but x was replaced by 0. So the result of evaluating this application is just the value 0. Okay, and then here's another example of an application. So in this case, we have the function, and then we have a value, and here we're just calling the value a. And then we actually have another value, which is b. So this is really 2 different applications. So it's the function and a, that's one application. And then the result of this, of evaluating the first application, is actually going to return another function. And the result of that, we put b, we apply b, we apply it with b. Okay, so the way this would work would be evaluated is you take the a and you put it in for the value x. So then everything on the body, that any place you see an x, it gets replaced by the value a. Okay, and then now we have a function that takes a y and returns an a, and we feed it a b into the function, and then we get back an a. So this whole thing, we say reduces or yields or evaluates to an A. Okay, and then finally, we have this notion of expression. And an expression can be either a function, can be an application, or it can just be a name. So for example, A is a name, the numbers 0 or 1 or 2 or whatever, that's also just considered a name. It's like a constant. So these are all examples of expressions in lambda calculus. So a function in and of itself is an expression. So here, this function takes an x and returns an expression e. Function application is also an expression. So here we have an expression e1 followed by an expression e2. So we're applying e1 to e2. And then just the name a would be an example of an expression. Okay, are there any questions about these 3 ideas?
Ooh, brave. Was that you,
Is
Tim?
anyone out there?
No.
Oh,
Ah, crap. I don't know what to do.
Actually, I had a question.
Okay.
So under 2, the function application, I'm having a hard time understanding how that second part reduces to A.
Okay. You want to work through that?
Yeah, that'd be great.
So let me pick, what's a good color? How about light blue-ish? Okay. So the way this works is we would start with the function, or the expression, right? Okay, so we're gonna, whenever you do function application, so let's say I have expression 1, expression 2, expression 3, you go from left to right when you do applications. So if we're gonna parenthesize this, we would do this first,
It's
the
me.
E1, E2 application
In
first,
the Zoom
and
class?
then we would do that, whatever that result is with E3. So down here, that's why I put these bigger parens in, because we're going to take A and we're going to apply it to the function first. So what we're going to do is we're going to pass A into the X, which means that this part goes away, this part disappears, and we're left with just the body of the function, but where X gets replaced by A. Okay, so the result of this one application is going to be lambda y dot A. And now we're going to apply that to the B. Is that clear? Does that make sense, that part?
Kind of.
That's the leap of faith right there.
Yeah.
Should I go over that again, or is that good?
That's fine. I'm just wondering why the B is sticking out. That just reduces. I guess I'm just not reading it right.
So no. So now we're here. We're at the point.
Connor.
Okay, so the B is now applied to the function. So passed into the function. So the B comes in to the Y, right?
Connor.
And then what happens is we just return the
Are
body.
you in class too?
But Y actually doesn't occur in the body. So that's why it just returns A.
Okay. That makes more sense.
Okay.
Right. Thank you.
Yep.
Would
You're
we
gonna
see later on
rip a
how
bong
this
in
works,
Zoom like that
in
one
cases
guy?
where the B would be ignored, even though is it like an optional variable into the function? Or
Well, I think so a good way to think about this, I just need some space. So I'm going to come up here. So this idea, like, let's say I have a function, lambda x,
That is a
lambda.
good question.
Why is it doing this? I'm hitting the N.
No idea.
Okay, so that's this here. Okay, what I just drew, and then so we have A, B. Oh, I think it's because I keep drawing out of the lines. Okay, A, B. So then this function, the way I think about this would be, so let's say we have a function over integers. We're just going to call it f. So we might say something like int.
I don't know what the fuck Warbeck's
F
talking about right now.
takes
He's talking about Starbucks or something.
x and an int
Something
y.
about business. Business.
And all this function does is it returns x. So from the outside, I just see f.
I should probably be
I
paying
see
attention.
a function f that takes
Yeah, but
two
just think of all the
arguments,
math you could
x
be
and
doing
y,
right
and it
now.
returns a value.
Math.
And so, I mean, really, these two things are exactly the same. It's just I'm calling this f. There's some slight differences, but for now, it's fine. So then what I'm saying on the right-hand side is I'm going to pass a in for the x. okay, or this way, and for the x, a goes into the x, and then the b goes into the y. And all I return is the x. So that's what's going on here. Super simple function. It's more complicated, I guess, than it needs to be, but it actually has a use, which is this idea of representing Boolean expressions, representing Boolean expressions in lambda calculus. Does this make sense? This kind of connection between the two?
Yeah, that makes sense. I wanted to ask, I know that you're posting lecture notes before each lecture now, but are you posting like this version, like edited versions? Would you be able to post those too?
I'm not sure. Possibly.
Okay.
Are you recording using a
It
third-party
kind of,
software? Because it's not letting me
it's a
record
little
without
tricky,
permission.
but I might be able to.
All right.
Yeah. I guess I'd rather, actually what I would prefer is just that people take notes maybe off of this, and then that serves as your notes. And then the lecture notes are kind of like the final version of the notes. My concern is if I do make a mistake here or something, usually I go back to the lecture notes as the main thing. And so I don't want to have like the same information multiple places, and especially if it's not 100% consistent.
Okay.
So I think what would be better is take notes off of this, and then use that with the actual lecture notes. Okay. Any other questions?
Tim, are you able to send that easily? Like after you record it?
All right. So
are you able to send it easily after you record it? Okay, because I was trying to record the class, but it says I need
so the
permission
next
to do it.
thing, I'm just gonna I wanted to give some examples of kind of how this works.
Okay, that'd be good.
And then also at the same time, kind of show or try to get this sense that you can do complicated things with lambda calculus. Okay, so
Oh no.
So what we did last time was we talked a little bit about Boolean expressions. So we started by saying that we're going to use two functions. So this function and this function.
So what you're saying is that if I say the word poopy butt, it's saved forever?
For true and for false. So here we just say T, capital T
Oh,
is basically just
no.
a stand-in for this function. So it's like a macro. T is just shorthand for this function, and F is shorthand for this function, and the big T and the big F, or the functions, represent respectively true and false. So this is just us choosing to represent the notion of true in a Boolean expression as this function. Okay. And these look very similar to the ones, what I was just describing, which is, so T is really lambda x, lambda y dot x, and then F is lambda x, and then lambda y dot y. So given two arguments, we return the first argument, that's true, and given two arguments, return the second argument, that's false. Actually, let me write these out fully. So just to avoid confusion. So this is really lambda x, lambda y x. This is lambda x, lambda y, y. This is true, represents true, and this represents false. Okay. And then basically I gave definitions for and, or, and not. So for and, we said that it is lambda x, y, x, y, lambda u, v, v, and really this is equivalent to lambda x, y, x, y, f, since this is really just f, false. So given two arguments, the and as a function returns x, the application x followed by y followed by false. Okay, and then or is very similar, so it's x, y, and then it's x lambda u v u in this case.
Jesus.
Whoop. And then y. And this is equivalent to lambda x, y, x, true, y. Okay. And then finally, negation is lambda x, x, followed by lambda u, v, v, followed by lambda y, z, y, and that's equivalent to lambda x dot x, false, true. Again, this is false, this is true. Okay. Everybody good so far? Any questions?
If you were to expand like one of the lower three, like you did in the blue above, like if you expanded and, can you do that real quick?
You and?
Yeah.
Yes. Let me do that. So and, whoops. And would be lambda x, lambda y dot x, y, lambda u, lambda v, v.
Okay, thank you.
Yep.
Are these things that you were just defining, or
Yeah.
is there?
Yeah. We're just making this up.
Okay.
Is that what you mean?
Yeah, I was confused. I was trying to figure out why they would be the way they are.
Yeah, why? I don't know. But it seems like it works. And we'll see that here in a second. But yeah, so the trick is, okay, we have now lambda calculus. It's this way to represent stuff, and it's very abstract. And then so the question becomes like, how do we use this? So the trick is, how do you kind of model lower level information using this? It's really not that different than in a Turing machine. It's just, I think people have a good intuition of how a Turing machine works and what's going on there. But for lambda calculus, it's a little less clear. And so really this is just an exercise in, here's a way to use lambda calculus to represent something a little bit more complicated. And we're using this notion of functions and function application in order to represent this stuff. So it's really not arbitrary how we're doing this, but it's just like we get to pick how we want to represent these things. So like we pick that we want true to represent this and false to represent this. We'll see it kind of just magically works. But that was kind of pre-planned. But it's really just like we're trying to use this tool as a representation for Boolean expressions. Okay.
Could we switch which one we called true and which one we called false, and then we just have to change and or and not?
Yes. Yeah, that's good. So if we we could swap these, for example, and then we just have to swap this stuff around, right? Like we can pick however we want to represent it. Okay, so I'm gonna give an example. I'm gonna erase this though for now, just so I have the space. And
Orbex
so
forgot to hit the record
I think
button.
we did a few of these last time. So I'm going to do true and true, which we know should be true, right? That should come out as true. So, the way, I guess the way we kind of rewrite this is we do and, we're going to use the and operator as a prefix operator. Okay, so we would do and, we can also even like put that in parentheses, and then that's the function. And then this is a function application with true and true. Okay, so I write T and T, and really what I'm doing is the and is this big function, and then I'm applying that function to its two operands, which are T and T. So if I come over here, and is a function, complicated function that takes two arguments, X and Y, and here T is the first and T is the second. Okay, so these are really the same thing. All right, so if I kind of follow this out, so expand this out, I'm going to use the definition of and, which is x, y dot x, y, f. I'm using, in particular, I'm using this definition, the more simplified version. Okay, and I'm applying this to true followed by true. So now I'm going to take the, that doesn't work. Sorry. I'm going to take, I'll just do the black here. So I'm going to take this and I'm going to basically put it in for X. Okay. So that's going to give me T. I'm sorry. Made a mistake. This is going to give me lambda y, because I got rid of the X, but I still have the Y. T, because the T gets replaced for the X, Y, F. So that's my function that results after one application. And then I still have one application left, which is on T. So now if I plug the T into the Y, I'm going to get T, T, F. Okay. And if I expand T back out to its functional form, I have lambda x, y dot x, T, F. Okay, so now if I plug T into the X, I get back lambda y dot, sorry, I plug T in for the X, I get lambda y dot T, because this X gets replaced by the T. And now I have the function, the F that I want to apply it to. And if I plug the F into the Y, what am I going to get back?
The T.
I get the T. And that's exactly what I wanted, because true and true should be true. Okay. Everybody good with that? So if I were to change this, and instead I'm going to replace this with F, so I come back, I'll start from here. Oh, one more. This is really like saying so I want to evaluate T and F, or true and false, which should result in false. Okay, this is the same again as calling it in the prefix version. Okay, so so I have everything the same here, but now I need to add in the F. Okay, so again, if I plug the T in to the function, I'm going to get back this expression. Everything stays the same, but now I have the F, the second operand. If I plug that in for the Y, this is going to give me TFF. Okay, so then on the next step, I expanded the T here, and so this is also F. Okay, so then I plug the F in for X, so that's going to give me F. And then if I do this final step where I plug the F in for Y, it still returns whatever the body is, which happened to be F. Okay.
If this were written as F and T, it would produce the same result.
Let's try it. Can we try it?
Yes. Okay.
So F and T. Okay, so again, I'm going to use the simplified version of and. So it's going to be lambda x y dot x y f. Okay. Whoops. And then I have F and T. Those are the operands. So then the F gets plugged in for the X. So that's going to give me lambda y dot F y F followed by T. Okay. So now if I plug the T in, I'm going to get F, T, F. And as a function application, I'm doing this first, right? And then I'm going to do the F part. So if I go back up to F.
All right, this stuff makes sense now, but I don't think it's going to make sense trying to code
X and
this.
basically discards the X. Right? It takes an X,
Okay.
and it takes a Y. The X gets discarded and the Y stays.
Okay,
So
because
up
this
here,
now
if
makes
I plug
sense.
the F,
So
I'm sorry, if I
hope
plug
it
the
translates
T
all right.
into the F, okay, that's going to basically just return a function lambda y dot y. Okay, so this returns lambda y dot y of f. And so now if I plug the f in, I just get back the f. The difference here is that when true is the first argument, we have a different looking function, right? Okay, whereas down here, because f is the first argument, the function looks slightly differently. Okay, so again, we get the same result. And if we do f and f, again, it'll be the same thing. Okay. In the lecture notes, there's a few other examples. I think I'm going to leave it there for now. They all of these pretty much work the same way, in that you can just kind of turn the crank and go through and plug the values in. So I think if you're still a little bit unsure of how this works, it would be a really good exercise to basically go to the lecture notes and do some of the examples and kind of walk through on your own, and then compare what you get back with what's actually given in the notes. Does anyone have questions before I move on to the next item? Okay. So, in order to be a proper, like a Turing complete language, there needs to be some notion of looping. So you need to be, if we come up with a programming language that has no mechanism for looping, then our language is, a general way to combine looping and branching really is what's required. So if we don't have a way to do that, if we don't even have a way to do looping, there's no way we're going to have a Turing complete language, an expressive programming language. So it turns out that in one way to simulate looping is to use recursion.
Animal Crossing, I hear.
So recursion is really just as powerful as any kind of looping construct. Anything you can do with a looping construct, like a while loop or a for loop or a do while or whatever, you can do using recursion. Okay, and so it turns out that in lambda calculus, you can do recursion. And so I wanted to just give you a sense for how that can work. Okay, so so I'm just going to walk through an example. And again, the key thing is not so much that you can come up with a way to represent
Maybe that's Animal
these
Crossing
things
you
in
hear.
calculus. It's really just, I would like you to have an understanding of how to kind of turn the crank
Haskell recursion
and do function application. So just basically being able to follow along with it, or if I even like on a quiz or an exam or something, if I were to say, here's the definition, here's some definitions in lambda calculus, show the result or the steps involved in doing these applications. That's really what I would want you to understand. So I'm going to just give you the definition of, or show you a way to define recursion in lambda calculus. And just all I kind of expect for you to understand is that as I go through it, you understand the steps that are involved, if that makes sense.
So
Yes.
are there things you can do with recursion that you can't do with loops then?
No. No.
No.
Yeah, good question. Okay. So here we go. Hold on tight. So
Oh God. I'm scared.
R is basically going to be used to stand for like kind of a generic shell
he told to
that
hold on.
you can plug a function into to recurse that function, to like call that function over
Tim,
and over
you should
again.
cuss again.
R is not in and of itself recursive. So it's doing something, it's mimicking recursion. Okay, so R has this structure. So it's lambda y, so it takes one argument, okay, and then the body has two functions that are applied within it. And they actually are identical functions within the body. Okay. So the basic, okay, so that's all I really need to say. I shouldn't have to say anything else. You should be able to see right away, this is recursive. Okay, but if you don't, let me just walk through it. So the basic idea is what happens is when you do an application of R. So let's say, so what I'm an example of that would be, let's say I have some function
Oh, it
f
says I
that
can't
I
send you
defined,
messages,
and
Jared.
I want to
What? Why?
take this
Because you're
this notion
offline.
of recursion, and I'm going to recursively call f.
Wait,
Okay,
did
so
you
I'm
get my
applying
message?
the function f to
Oh,
r.
damn.
I gotta pay
What
attention to this part in
happens
the
is
lecture.
every
It looks
time I
important.
do one application, I kind of evaluate one application of
So that's the power of friend
applying
settings.
f to r, or
You labeled me the
basically r
pervert or
takes
something.
f as an
No, I can't
argument.
message you.
That
Heh.
R has this magic thing that it regenerates itself. Okay, so it's basically regenerates the R and this function, but it goes like an additional step to making a call. Okay, so the nature of the way that R is defined is it's regenerative.
Okay.
This is kind of the property of R. All right, so we can just walk through kind of an application just so you can see that it's doing this regeneration. All right, so I'm going to define this notion R sub f as, so I'm just going to use just equality instead of equivalence here. So RF, but it's really just the same. I'm just simplifying a little bit. So I'm going to give basically, well, I'll just write it this way first. So I'm going to take R and I'm going to make an application out of it with F. Okay, so if I write out R, I end up with all of R here. And then I'm applying it to F. So that's sort of step one, the first kind of just rewriting R sub F, or R applied to F. Okay, so then I'm going to pass F into Y. Okay, and then all of the Y's are going to get replaced by F when I do that. So I'm going to do one step in the application. So I take F and I substitute F in for Y. So that's going to give me lambda x dot F XX okay, and then lambda x, the same thing repeated, F XX. The first application, basically. So the key thing here is this is not F apply. This is not a function call with two parameters necessarily. This is really just a bigger function application. Okay. All right. So then I have this function and this function in a function application. So what I'm going to do is I'm going to plug this one
dude.
We're all in a class.
to X.
Are you here to join us in class?
Oh,
Okay.
yes.
I'm
No, I was
take
going to ask,
this,
do you guys do the medical imaging
right
homework?
hand side, and I'm going to do
We're like
one
halfway
step in
through.
the
We haven't done
application.
3.
So this whole thing comes in
No,
for
I was just
X,
wondering,
so that's going to put
have you
F
done like
on the outside. So this F
reference
goes
graph?
to the
The graph?
outside. And then the two
Yeah, I ended up
X's
looking
get
like
replaced,
an M.
each one by one of these again.
Hero stream.
Okay, so this is becomes lambda X F XX lambda X F X.
Just give it a bit to like load, I guess.
Right.
That's step 3. Okay, so
Looks like an M.
here's kind of the important
So what did you
step
get?
to
Well, let me
understand what
show mine.
all of this nonsense is doing.
All right, here I gotta
Which
stop
is
streaming
that
for you stream.
if we
Alright,
look here, actually I'll put the
Go for it.
quality back.
Love you,
Maybe
Tim.
that makes it a little bit easier to understand. So R of F, I said, is equivalent to this line 2 here. Okay, so when I look, what I see here is exactly line 2. And so what that means is I can replace what's in this with R sub f. So that gives me f applied.
Where'd you get the other two from?
F. Okay.
Does it come from
So
does it come from changing the
then I
A
can do
and
the same thing again. So I know here R sub f. R sub f is actually equal to this whole thing on
oh,
line
you're
3.
plotting all of them.
And
You're
so
plotting
this
f
gives
of
me
x and
f
5 as well.
with f again applied to R sub
How is
f.
he able to drag out that f in step 3?
Right? So that's one application. I can do it again. Here, I can replace this with another f of R sub f. So I end up with f of f
Excuse
of
me?
f of R sub f. Yes?
Sorry to interrupt, but on step 3, how'd you pull out that f again?
This
On
one?
the all the way to the left, yeah. Yeah.
Yes. I took all of the right-hand side of this. I took all of this and I plugged it in for x. And so that left just returned the body, which started with f, and then had these two things as replaced for the x's.
Okay.
Okay, so there's absolute silence from everybody, which is fine. So the point is, and hopefully you can see this, the nature of this definition is regenerative in the sense that as I do these applications, so basically like once I go through this process and I get to this step here, because I've gotten back to where I started, which was R sub f, I can just keep applying this as many times as I want. And so it's effectively, I'm calling f over f over f over f as many times as I want. And so what I've done is I've now created a loop, what looks like a loop. It's really recursion.
So is there any function we can apply R2 that won't recurse infinitely?
Yes, and the way, okay, I'm not going to go through that, but the way we would stop the recursion is to mix back in something very similar to the Boolean operations. So these Boolean expressions could be used, something like that could be used for example, for a conditional statement. And then in that case, based on the evaluation of that Boolean expression, we would maybe return at the function f, which would then allow us to keep recursing, or we could do something that wouldn't do that based on the Boolean expression. So if we basically mix Boolean expressions with this definition of R, then we can stop recursively calling f. So that's the basic idea. So if we combine these things, now we have a language that can do Boolean expressions. It's not hard to imagine we could do conditionals using Boolean expressions. And then we have recursion. So we have basically the full power of Turing machines. So lambda calculus and Turing machines have the same expressive power. And this is something that was actually proved many, many years ago, that they're really describing the same sort of computational characteristics, and they have they're basically two different ways to model the same kinds of computations that can be done in each respective language or paradigm. Okay, so again, this is pretty abstract. So what I expect for people to understand from this, I don't expect you to be an expert at lambda calculus. I do want you to have a general sense of what it is. And if I give you sort of expressions or have something sort of set up like this, for example, and then I might ask you to do, do the function applications to calculate what the result of something like that would be. So I want you to understand it enough to be able to do these function applications. And then hopefully it's somewhat not out of question that really this very simple language of lambda calculus can represent very complicated things, including recursion and Boolean expressions and conditionals. So does anyone have questions before I move on?
So as far as equivalent expressive power goes, do you say that, or could you say that any Turing machine can be represented by a lambda expression and vice versa?
Yeah, exactly. Yes, that's right. Well, in fact, yeah, we'll leave it at that. That any Turing machine can be represented as in lambda calculus, and then any kind of program in lambda calculus could be represented as a Turing machine. Are there other questions before I move on? Okay, so the purpose of this wasn't to torture you. It really was, I think it's important to have a sense of what lambda calculus is because it forms the underlying computational model of functional programming. And so what we're going to do now for a big chunk of the rest of the semester is we're going to start talking about a programming language called Haskell. And so Haskell is a functional programming, is a language that really very closely follows this lambda calculus and this notion of the functional paradigm. So there's many different functional programming languages, but what's nice about Haskell is that it does sort of closely follow lambda calculus or the notions that are in lambda calculus. The syntax is also very simple. It's almost like Python-like in terms of the syntax, but behind the hood, it's really doing all this lambda calculus stuff. So I think it's good to really, it kind of jumpstarts your understanding of what's going on in Haskell to have a sense of lambda calculus. Okay, so what I'm going to do now for the last few minutes here is I'm going to just talk about some of the main features of Haskell. Okay, some of the main features. And in terms of a functional programming language, it's not any one feature that makes Haskell unique. It's really that it has these combinations of features that is what kind of makes Haskell shine to some degree. Okay, so the first kind of major feature of Haskell is it's what's called a purely functional language. And what that means is that in Haskell, you effectively only have what are called pure functions. And so when we say a pure function, we're talking about a mathematical function where in a mathematical function, unlike in a programming language, for any particular input to that function, you always get the same result. So if I have a function like called f, let's say, and I pass in a value to f, it's for that value, f always returns the same result. Okay, so that's what's meant by a pure function, is that it's similar to the notion of a mathematical function. Okay, so there's a couple of, there's one kind of aspect of this that you'll hear about when it comes to Haskell, which is that in Haskell, functions do not have side effects. Whoops. Okay, and what that means is that functions don't modify state, or they cannot modify state. So I'm going to give you just a really quick example of a function that does modify state. And I'll use like a C-like language to do this. So this would be an example of a function that is not pure. Okay, so first of all, I declare a global variable x, and then I'm going to define a function f. It takes one argument, a y. It adds x and y and stores the result back into x, and then it just returns x. Okay, so so somebody tell me what happens when I call f of 1? What is the result?
It's just 1, right?
1. It returns 1. Okay, so if I call f of 1, it's going to return 1. What if I call f of 2? What does it return? Somebody tell me what it returns.
Depends what you called f with previously.
I call actually this is it. I called f of 1. Yeah, it does depend on what I called it previously. So let's say I called f of 1, okay, and then I called f of 2.
Class over
so
yet?
Right after. So I
Losers.
say f of 1, and then on the next line I say f of 2. So what gets returned?
I'm gonna go to the bathroom.
3. Good. Okay. What happens if I call f of 1 again? Right after I called, so I called f of 1, then I called f of 2, and now I called f of 1 again.
4.
4. Okay, so this is an example of a function that's not pure. It's not a mathematical function, right? Because for different inputs, I can get different outputs. And the reason why it's happening in this case is because x is a global variable. And within f, I'm modifying this global variable. And I'm using it, x, to actually do the calculation for the function, or what the function returns. And so in this case, the x, the global variable, is what's referred to as state. And so f, as a byproduct of calling f, I'm modifying the state. I'm modifying this global state. And we say, when that happens, we say that f has side effects. So the side effect of f, of calling f, is that it modifies global state in this case. And so f has a side effect, and it uses this to do its computation, and so it is not a pure function. So in Haskell, f, you cannot define a function that looks like f. It is not possible to do this. So you can't do something like this in Haskell or in a purely functional language. Are there any questions?